Hello everyone. Now we are going to discuss about the topic called electronic voting with cryptography. What is meant by electronic voting? In cryptography, e-voting refers to using cryptographic techniques to build secure electronic voting systems. Our goal is to allow voters to cast their vote electronically through computers, mobile phones, or voting machines while ensuring the fundamental security requirements of voting are preserved. Voting is the foundation of democracy, ensuring the citizens have the right to choose their leaders. Some of the traditional problems we are facing in the traditional methods are tampering of votes, booth capturing, lack of transparency in counting, human errors in management. These can be resolved by using the upgrowth digital technology. The traditional challenges, other traditional challenges are traditional paper ballot systems. While familiar, often grapple with issues like manual fraud, high operational costs, and slow vote tallying process. These inefficiencies can undermine public confidence and delay crucial democratic outcomes. Why e-voting needs security? E-voting means casting votes using electronic systems like online platforms or digital machines. However, e-voting introduces new risks: cyber attacks, unauthorized access by insiders, voter impersonating. So we are using cryptography in this. The promise of e-voting leverages modern computing and network technologies to streamline the voting process from casting to counter. However, its adopting hinges on addressing fundamental concerns, ensuring security, maintaining trust, guaranteeing transparency, and preserving voter anonymity. Cryptography is the indissoluble foundation for building robust and trustworthiness the e-voting systems. Now we are going to see why cryptography is essential for e-voting. For e-voting systems to be truly effective and gain public trust, they must uphold strict security principles. Cryptography provides the mechanisms to guarantee these critical properties. The first one is confidentiality. Confidentiality is ensuring that individual votes remain secret and cannot be linked to the voter. The meaning for this is no one should know how an individual casted his vote. For example, a student votes for candidate A in college election. The vote is encrypted with election authorities' public key. Even the server storing the ballot cannot read the vote until decrypted at the end of the election. The second one is integrity. Integrity is guaranteeing the cast votes cannot be altered or corrupted after the submission. Once a vote is cast, it must be not be altered or deleted. For example, each vote is stored with a cryptographic hash. If an attacker tries to modify a vote from A to B, the hash will no longer match and tampering will be detected. Third one is authentication. Authentication is verifying that only eligible and authorized voter can cast a ballot, preventing impersonating. Only eligible persons can vote, cast one voter. Before voting, a voter uses a digital signature with a private key. The system checks the signature using the voter's public key to confirm that vote really came from the registered voter. And the fourth one is anonymity. Anonymity means voter cannot be linked to voter, protecting the voter's identity, ensuring no correlation between a voter and their specific voter. Using a blind signature scheme, the election authority signs to voters' ballot without saying its content. This way, the voter can submit a valid ballot, but the authority cannot link it back to them. And the fifth one is verifiability example, meaning voters and observers can verify the election without violating privacy. Verifiability means allowing voters to confirm that their vote was accurately recorded and counting without compromising anonymity. After voting, the system gives the voter a receipt ID. Later, the voter can check a public bulletin board to confirm their encrypted vote is included in the tally. At the same time, auditors can verify that total tally using zero knowledge proofs without knowing who voted to whom. In this slide, we are going to see about key cryptography techniques for e-voting. There are various cryptographic protocols and algorithms are combined to secure the entire e-voting lifecycle. The first one is public key encryption. The public key encryption is secure the transmission of votes, allowing voter to encrypt their ballot with the public key on the election authority can decrypt. Used to encrypt votes so they remain confidential until tallying. Example, voter encrypts the ballot with the election authority's public key. Only they can decrypt with the private key. The second one is homomorphic encryption. Enables voters to be counted while remaining encrypted, preventing any party from learning intermediate tally results until final decryption. Allows tallying of encrypted votes without decrypting of individual ballot. Example, if yes is equal to 1 and no is equal to 0, encrypted votes can be added together to get the total count without revealing each person's choice. The third one is digital signatures. Authenticates voters and prevent double voting by cryptographically tying a vote to authenticate voter without revealing their identity. Ensures authentication and no repudiation. Only legitimate voters can cast vote and they cannot later deny casting. Example, a voter signs their encrypted vote with a private key. The system verifies with their public key. Hash functions is used to create unique fixed size digital fingerprints of ballots, enabling tamper detection by comparing hashes before and after storage. Ensures integrity of votes, detect if any vote is altered. Example, each vote is stored with a hash. If tampered, the mismatch reveals fraud. Zero knowledge proofs provides verifiability without revealing votes. Example, the system can prove that your encrypted vote is included in the tally without showing your actual choice. Blockchain technology. The blockchain technology is also called distributed ledger. Provides a tampered proof record of votes and provides an immutable, transparent, and distributed ledger for recording votes, enhancing auditability and resistance to single point failures. For example, each vote is added as a block in a chain, making alteration or deletion practically impossible. In this slide, we are going to see about workflow of cryptographically secure e-voting system. This simplified diagram illustrates the journey of vote through a modern e-voting system, highlighting cryptographic touchpoints. The first one is voter authentication. Voters use secure digital IDs, biometrics, or smart cards to prove eligibility. Each eligible voter is registered in this system. Voter receives cryptographically credentials that means keys or certificates. Here, the cryptography is used in digital signatures, public key certificates. And the next one is vote casting. The voter's ballot is encrypted locally using a public key encryption. The voter submits the encrypted and signed ballot to the ballot box, the server. Vote is stored securely with hash to prevent tampering. The cryptography used is hash functions, integrity, blockchain, blockchain imputable of storage. This may be optional for this case. Transmission. The encrypted ballot is sent over a secure authenticated channel. Storage. Encrypted votes are recorded as a tamper-resistant database or distributed ledger blockchain. Counting. Counting. Votes are tallied using advanced techniques like homomorphic encryption or mixed nuts to present the final result. Encrypted voters are tallied using homomorphic encryption, so counting can be done without decrypting each voter. At the end, only the final tally is decrypted. And the last one in this workflow is result publication. The final tally is published in a verifiable and audited manner. Each voter can verify that their vote was included in the tally via a ID receipt. Observers or auditors can verify correctness using zero knowledge proofs without seeing individual votes. In this slide, we are going to see about diverse approaches to e-voting. What are the approaches to e-voting, sir? E-voting system manifests in various forms, each with unique characteristics and security consideration. Direct recording electronic machines DRE. Standalone voting machines that record votes directly into a memory, often without a paper or trail, debited for auditability. Internet voting I-voting allows voters to cast ballots from any internet connected devices. Offer in con- Offers convenience but faces significant security challenges for remote authentication and coercion. Mobile app voting. An experimental subset of iVoting is mobile app voting. This is used in dedicated mobile. Raises similar security and device integrity concerns as general iVoting. The third one is blockchain voting, an emerging model leveraging blockchain voting for transparency. Advantages of cryptographically secure e-voting. When properly implementation, e-voting system offers several benefits to the democratic process. First one is faster tallying. Significantly reduces the time required to count and announce election results. Reduce human errors. Minimizes mistakes associated with manual counting and data entry. Enhances accessibility, enables remote voting for citizens abroad, military personnel, and individuals with disability. Transparency and auditability. Cryptography methods and blockchain can provide robust mechanism for public verification. And this is tamper resistance. Leverages encryption and distributed ledgers highly resistant to unauthorized modifications. Although it has several benefits, it also has challenges and risks. First one is cyber security vulnerabilities. Risk of malware, denial of services, DOS attacks, and inside threats impacting system availability and integrity. Voter coercion, especially in remote settings like iVoting, it's harder to prevent individuals from being pressured into voting a certain way. Digital divide. Not all citizens have equal access to technology or digital literacy, potentially disenfranchising of the population. System complexity and trust. Cryptographic systems are inherently complex, making it challenging for public to fully understand and trust their security. Scalability. Ensuring an e-voting system can handle the immense volume of votes for larger national elections without performance degradation or security compromises. The real world e-voting implementations are Estonia, Switzerland, India, US, and EU. Estonia, a global leader implementing large scale e-voting since 2005, known for its robust digital ID infrastructure. Switzerland, actively exploring and piloting blockchain based voting solutions at municipal and cantonal levels. India investing blockchain for specific use cases such as facilitating voting for migrant workers across state lines. US and EU. Various pilot programs and research initiatives are being tested to explore secure online voting. However, widespread adoption faces significant challenges, including security risk and legal regulatory debates over election laws, public trust issues. Case study of Estonia's pioneering e-voting system. Digital ID Foundation. The system relies on mandatory, highly secure digital ID cards with integrated cryptographic keys for voter authentication. End-to-end encryption. Votes are encrypted from the voter's device to election servers, ensuring confidentiality. Voter verifiability. Voters can use smartphone app to verify that their encrypted vote was correctly received and recorded on election servers. Anot- Anonymization before counting. Before tallying, votes are anonymized through a mixed-net process, severing the link between the voter's identity and their ballot. Lessons learned. Lessons learned from Estonia's experience. Estonia's experience highlighted the public trust built through the transparent process and robust digital infrastructure is a critical as the underlying cryptographic security. Ongoing audits and public educations are the key. This is a short summary of e-voting with cryptography. First one is secure authentication ensures on only eligible voters cast their vote. Encryption like RSA, ECC homomorphic protects vote privacy. Hashing and secure channels guarantees integrity during transmission. Blockchain secure databases provide transparency and immutability. Homomorphic encryption mixers allow tallying without exposing individual votes. Zero knowledge proofs enables verifying but private election results, ensures privacy, integrity, and transparency and trust in the voting process. E-voting with cryptography is equal to secure, transparent, and verifiable democracy. And thank you all. This is A. Jayakash 23 MIA 1092 from VIT Chennai.